Fourth try! This is the podcast for Physical Science 8th grade, chapters 3.1 and 3.2, regarding motion and force!
Alright, first up we're going to talk about measuring motion, specifically speed and velocity. So first up we will talk about speed. You need to remember that speed is a measure of how fast something moves through a particular distance over a definite time period, right? So speed is distance divided by time. So the greater the speed, the faster the change in position. So greater the speed, faster position change. Remember how speed and position, how they work together. What does one have to do with the other? How are they similar? In order to calculate speed, you have to know both distance and time. So let's take a look at this picture. In this picture, you can see that we have to know both distance and time. So here's our distance, right? And these are our time frames. So what this is saying is this first rider has gone 8 meters in distance in 2 seconds, while this second rider has only gone 4 meters in 2 seconds. So this way we're able to calculate their speed. In order to find the speed, we just have to know that distance and time, also known as S equals D over T. Speed equals distance divided by time. So like if we go back to those bikes, we know that a object, if it travels the same amount of distance, but it took a shorter amount of time, it has a greater amount of speed. So it's going to have gone faster. If we take a look at this example from the textbook, right? If we have a wheelchair racer that completes a 100-meter course in 20 seconds, what is his speed? So again, a 100-meter course in 20 seconds. So distance equals 100 meters. Time is 20 seconds. We're trying to find out speed, so we're going to use our formula of S equals D over T. Put those numbers in, right? So we've got 100 meters over 20 seconds. Calculates out to 5 meters per second. Now our unit is in meters per second. Unit of speed is meters per second, so they agree. So therefore we have that our speed is 5 meters per second. All right, take a look at this distance time graph. Remember, distance time graphs are very important in science and in math. And so what you'll notice is this first section, it says, the zebra's just walking. So his speed isn't great. He's going a short amount of distance in a matter of time. So in this case, he went 40 meters in 20 seconds. So he's just kind of walking along. Then he takes a stop right here in the center from steps 2 to 3, where he stops and he has something to eat. And then a lion comes by, so he's going to increase rapidly. And you're going to see that in the time graph. You're able to tell these things in the distance time graph by when you see the lines changing position.
And force!
All right, next up is velocity. And let's remember the definition of velocity means that it has both a size and a direction, which, as you know, should be a vector because it has both. So remember that velocity is a speed in a specific direction. Let's say you're walking in a specific direction, in this case east, at a speed of 3 meters per second. That is a velocity. So let's take a picture of these ants here, or take a look at this picture. So this ant moving slowly uphill, he is going at a slow velocity in an uphill direction. The ant moving down is a quick downward movement. And then our last one is moving at a medium speed at a straight direction. So remember that our velocity and speed, they're related, but they're not the same thing. Let's take a look at this picture here. And this is a picture of a couple of trains traveling at a specific speed. So each train, if you were to go both north and then come back south, each train is traveling at a specific speed. However, the velocity would be different because the direction has changed. All right, next up is acceleration. And let's remember the definition of acceleration. is the rate at which velocity changes over time. Okay, make sure that you note that velocity, if it doesn't change, so if you do not have a rate of change over time, then there is no acceleration that is occurring. Now, we talked about this before, where we understand typically in our everyday language that if we say the word acceleration, we expect that to mean that we are speeding up. Well, again, in physics, that does not mean the same thing, right? In physics, it's different, right? Acceleration refers to any change in velocity. In physics, it means a change in velocity, no matter the direction of that change. That could include a change going in the same direction as the motion, a change in the opposite direction of the motion, or a change at a right angle to a motion. In order to calculate acceleration, you need to know the velocity and the time, and that has to actually be a initial velocity subtracted from the final velocity divided by time, also known as A, meaning acceleration, equals V final, so velocity final, minus V initial, velocity initial, all divided by time. Remember that when we're looking at velocity or acceleration actually, then this is actually written out using the meters per second squared, because a standard unit for acceleration, right, is in meters per second. But if you're looking at per second over time, then you're looking at per second or meters per second per second. So again, meters per second squared. And the last thing for this section is I'd like to talk about velocity time graphs. So in here, again, if we're looking at a velocity time graph, we've got time in seconds on the bottom, and we've got velocity in meters per second on the y-axis. And as we can see by this image, we can see that there is a change in velocity over time. So unlike our last graph where we're looking at the distance over time, in this case we're looking at velocity over time. So in this specific thing, we're looking at a student pushing on a scooter, right? So at first he has a positive acceleration, so we see a vast increase in that. Then for a time he's staying at the same acceleration. Okay, and then he is going to come to a stop in which he is going to have negative acceleration. All right, next up is lesson 3.2.1, in which we're going to talk about the nature of forces. And the very first thing I want to talk about is to remember the definition of a force, and that is a push or pull. So anytime that you are changing the motion of an object, you're going to use force. Take this picture of this skater here, right? They have the contact force occurring down here when the skates push against the ground. We have a gravity force that is pulling the skater towards the ground. And then there's a friction between the wheels and the ground, which is again another force. So just like velocity, force is a vector because it has both a size and a direction. So when we have multiple forces that are acting on an object, you're going to be able to predict the change that that object's motion is going to take. Okay, so the net force is the overall force that acts on the object when forces are combined, such as here in this picture, right? We've got balanced forces and unbalanced forces. If the balanced forces are equal, so we've got equal amount of force being applied from different sides, that means it is a balanced force, right? There's no effect. It's going to stay the same. Take a look at this picture here, right? This ball is going nowhere. However, in unbalanced forces, like the one here where you have one player that is forcing the ball further than the other player can hold it, this is where you're going to get that change in motion. All right, let's talk about Newton's laws. Remember, he has 3 of them. And the very first one, we're going to handle it now and then we'll talk about the others a little bit later. The very first law is that objects at rest tend to stay at rest. Objects that are moving tend to continue moving unless a force acts upon them, right? Again, Newton's first law states that objects at rest remain at rest, Objects in motion remain in motion with the same velocity, remember, unless they're acted upon by that unbalanced force. For instance, if this ball, the soccer ball, right, it's sitting here, is there anything going on to it yet? No, so it's going to stay at rest. However, the soccer player's foot is going to become an unbalanced force that is going to act upon that balanced force of the object at rest. Same idea over here in this other one about objects in motion, right? If the object is in motion, it's going to continue on with the same velocity, continue on within that motion, unless it's acted upon by that unbalanced force, in this case the goalkeeper, that would put a stop to that motion. Last part for this section regards inertia. Okay, remember that inertia, this is the resistance of an object to a change in the speed or direction of its motion. Right, again, go back to Newton's first law where he talked about the tendency of an object to resist change in motion. This is also known as the law of inertia. So when you measure the mass of an object, you're measuring its inertia. Okay, when you're in a car, you are going to move forward with the car because you have the same inertia at that time. However, if you were to step on the brakes, the car is going to stop, but you are going to continue forward. That's why we wear seatbelts, is so that we actually do not continue with our inertia. Okay, the windshield in this case, if you were not wearing your seatbelt, applies that unbalanced force, which is going to stop the driver's forward motion, stop their inertia. All right, Newton's second law has to do with force, mass, and acceleration. So he observed that acceleration of an object depends on the mass of the object and the size of the force applied to it. So the acceleration of an object increases with increased force or decreases with increased mass. Okay, so let's take a look at this first picture, right? We have a small force and a large force, both going on the same amount of mass. So this means that because we have a small force on a mass, we have a large force on the same mass, the large force is going to have the greater amount of acceleration. Now over here, we have a small force and a small force. We have a small mass and a large mass. And so in this case, the boy with the small mass is going to have a greater amount of acceleration than the boy with the large mass. In order to calculate force, we need to take mass and multiply it by acceleration. This is also written as F equals ma. In order to calculate force, you need to have these same things, but you can actually calculate force, mass, or acceleration as long as you know at least two of these items. Remember that if the same force is acting on two objects, right? The object with the less mass is going to have greater acceleration. If an object loses mass, they can gain acceleration if the force remains the same, right? If we were to lose mass, say, again, back to our grocery baskets, if we were to take some of those groceries out, then that grocery basket can actually gain acceleration if the same amount of force is being applied to it. Centripetal force is the force that keeps a motion going around in a circular pattern, right? The force points towards the center of the circle. Make sure you remember that. The force points towards the center of the circle, and without that centripetal force, the object would go flying off in a straight line. Think back to when we had our classmates that were moving around the classroom, and one flows off into one direction. Or swinging around the roll of tape on a string, and if you let go, it's going to fly off in the same direction that it was heading. It's not going to continue that central motion if it loses that centripetal force. So again, a centripetal force is any force that keeps an object moving in a circle, and remember that force is going towards the center of that circle. All right, and Newton's third law is the last of his laws. And we know that Newton's third law relates to action and reaction forces, right? He observed that if you were to see a jellyfish or any creature that uses a motion, such as the jellyfish does, then you would see that they always have a reaction action pair. They always act in pairs. Those forces act in pairs, right? So let's remember that Newton's third law states that every time one object exerts a force on another object, the second object exerts a force that is equal in size and opposite in direction back on that first object. We often say this differently. We say for every action there is an equal and opposite reaction. And we call these action and reactions. We call them action and reaction pairs, right? One of the items is called the action force and the other is called the reaction force. So if we're thinking about this jellyfish, right? The jellyfish, as it pushes water away from its body, that is the action force. And then the water pushing back on the jellyfish in order to move is the reaction force. Think back to when we let loose the balloon in class. When we let loose that balloon, we've got air pushing out of the balloon, which is the action force, and the air pushing the balloon forward is that reaction force. Remember now, a balanced force is different than an action and reaction force, right? A balanced force acts on a single object. An action and reaction force acts on different objects. Here's another look at Newton's third law. If we have two skaters on wheels, obviously, and one pushes off of the other, then they're actually both going to move. We don't just push off and this person goes forward. No, instead, this person in the front is going to go forward, but the person in the back, this girl, she's going to go backwards because of that reaction-action force. This kangaroo is a good representation of actually all of three of Newton's laws of motion, right? So the very first one is Newton's first law, in which the gravity is affecting the kangaroo. If no other force were acting on this kangaroo, such as gravity, then when the kangaroo jumps, he would jump and just keep going. That second item has to be acting upon him to change his force. If we take a look at the large kangaroo and the small kangaroo, if they each exert the same amount of force, then the small kangaroo is going to go further because it has less mass. And then if we take a look at this last one for Newton's third law, then what you can see is that the action and reaction force is in effect every time the kangaroo jumps off from the ground. It has an action force pushing off from the ground and a reaction force pushing it forward. All right, our last section is momentum. And momentum, remember, is the measure of mass in motion. Momentum is similar to inertia because inertia and momentum both have to do with the mass of an object. However, unlike inertia, momentum actually takes into account how fast that object is moving. So the formula for momentum is P, which is momentum, equals m times v, mass times velocity. So for instance, let's take a look at this problem here. So what's the momentum of a 1.5 kilogram ball moving at 2 meters per second? So our mass is our 1.5 kilograms. Our velocity is our 2 meters per second. We're going to pop that into our formula here, in which we're going to get P equals 1.5 kilogram times 2 meters per second. Calculate that out, and you get 3 kilograms per meter per second, also the answer. All right, let's talk about collision for a moment. Collision, remember, this is where you have two items, objects that come into close contact with each other, and they're going to exchange energy. So think back to when we talked about the bumper cars. And when you push yourself into a bumper car, think back to when you've been in a bumper car. When you push into another car, then what's going to happen is you are going to continue forward, and that bumper car is going to continue forward. You're actually going to shake back a little bit too. So you're transferring some of your momentum, some of your energy. As you're pushing forward, some of your energy is transferred to the other car. Slows you down, speeds them up, but you have the same energy between the two. Now, if one of those cars was tiny and one was big, let's say we've got a bumper car and a regular car, right? And they're affected by a collision, then because of the different masses, the one with less mass has a greater change in velocity. Remember back to the bowling ball and the small ball. As the bowling ball is pushed forward, it's going to have a greater effect on this while it just slightly slows down. So again, let's take a look at this picture again of those bumper cars. So if we have the two cars moving, before the collision, the momentum of that first car is going to be the greatest, greater than the momentum of the second car, right? But their combined momentum is a total momentum of the system. We add the two together. Now, during the collision, the forces on the two cars are equal and opposite, right? Just like Newton's third law states. And the momentum is transferred from one car to the other during the collision. After the collision, the momentum lost by the one car, gained by the other car. So this second car is now going to go faster than the first car because it gained more momentum. At the same time, that total momentum in the system, it's still going to stay the same. Okay, little momentum, big momentum. Equal momentum is just going in different directions. Now we've got little and big. This is actually a representation of the conservation of momentum. This conservation of momentum principle states that the total momentum of a system of objects, it does not change. As long as no outside forces are acting on that system, you're going to have the same amount of energy in the system. When two cars collide during a crash test, momentum is conserved during that collision. So like we talked before about the bumper cars, this is going to be a little different because the two cars, like the ones in this photograph, they're going to stick together after the collision. Even in this case, the total momentum of both cars together, it's still going to be the same total momentum of both cars before that collision. So before the crash, the yellow car in this picture had a certain momentum, and the blue car, it had no momentum. It was sitting there. After the crash, the two cars moved together with a combined momentum equal to the momentum that the yellow car had before the collision. It's like we talked about before. If the yellow car has 100% of the momentum, when the two items combined, it's going to transfer some of its momentum to the other vehicle, and they're still going to be at 100%, the difference being that now, let's say the blue car has a 40% of the momentum and the yellow car has 60%. One final thing to think about here is the idea that momentum is conserved whenever there are only the two forces, the action and reaction force pairs that are affecting it. However, like we've talked about with this picture, when we're looking at the firemen, the hose and the water, it's that outside force that is causing the force or causing the momentum to be changed here. In this case, you're not going to conserve your momentum.